this was a requested topic, and I thought that we could just go through it casually together. I jotted down some notes from the comment just so that I can keep track of what I'm looking at and what I'm trying to answer today, but this might or may not make sense to you right now, so that is totally okay. Before we get into it, for context, this is a topic from calculus. If you just so happen to be learning calculus in high school, this is in the AP Calculus BC section, if that means anything to you. But otherwise, no matter. Just wanted to kind of place this topic in context. So, as always, you're welcome to just sit back, relax. I'll just be doing some math here. It doesn't matter if you like it or don't or whatever. I just hope that you can sit back with some whispering, maybe zone out, maybe drift off to sleep, and I hope that I can say something helpful to our friend here of the channel who requested this. Okay, so Lagrange Error Bound. So finding the degree of an expansion that makes the error less than a certain value given an x value. For example, what degree McLaurin series expansion for cosine 1 would have an error that's less than 0.001. So if you've done problems like this before, then this might make sense, or at least you might get the gist of what they're asking for. But, you know, we'll just take it from there and see. So, first of all, what is an error? So let's start with the actual Lagrange Error Bound part. What is an error? What are we bounding? So, just from the most basic idea, errors come up when we approximate something, right? So if we have an exact value, an actual value, and then we try to approximate that value, there's going to be an error. If our error is 0, that means we got it exactly right, but there's no need to approximate at that point, right? So in general, we might have the actual value for something. In this case, we'll have f of x at a particular x value. We'll have an approximation of that value. And then we'll have some type of error, and so we might overestimate or underestimate, depending. So then we'll have plus or minus some kind of error. So the error itself is going to be positive. That's why we account for plus or minus this positive value. Okay, so another way to rewrite this is that our error is the absolute value, which just means to take the positive difference between actual minus approximation. Alright, so that's just big picture idea. So in this particular case, we have actual is going to be our function f of x at a particular x value. So you just plug that x in like we would in algebra. Our approximation is going to be our Taylor series / polynomial to a particular degree, an n degree. In this case, this person wants to look at the McLaurin series. That's just a special case of the Taylor series. It's just a Taylor series about 0. So we use Taylor / McLaurin up to a particular degree, a finite degree. So polynomial to n degrees. So if we were to do this infinitely, that infinite sum is the expansion of our function. That would be exact. But because we're going to stop at n degrees, there's going to be the rest of that series, and that is our remainder. That is our error. So you can see actual is f of x, approximation is our Taylor polynomial to n degree, and I'm going to write that as pnx, like that, and then plus or minus our error, and that's what we're bounding. So of course you should adapt notation to whatever you're familiar with. Sometimes you'll see like Tn of x or whatever, but I'm just doing p for polynomial and x, r being for remainder, and this is the remainder or the error after you've done Taylor or McLaurin polynomial to n degree. So this n corresponds to this n degree, okay? And I know that's a little confusing because the remainder, as we will see, has to do with n plus 1, but this n is related to this n, okay? So that means that we have our error, just following this analogy here. So error is going to be the absolute value of this r and this remainder, which is the difference, the absolute value of the difference between f of x and p and x here. Okay, so from here, this is just going to be a reminder of what a Taylor polynomial is. How do you expand this? So we're going to assume that every piece is differentiable. We're going to assume that all the conditions are fine for the function that we're looking at. And in this case, cosine is fine to do. All the derivatives exist, and so in this case we're going to look at what Pn is, just to go over Taylor polynomials again. Alright, so I guess I'll just do it here. So the Taylor series, just to get this pattern down, okay? So it's f of a particular constant c. For McLaurin, c is going to equal 0, but we're going to do a general Taylor series here. You can do with 0 factorial to make the pattern even more clear, but I'm just going to stick with this. It's fine. F prime of c x minus c to the power of 1 over 1 factorial, which you don't have to write, plus f prime prime c x minus c squared over 2 factorial, plus, we'll go to the third derivative, x minus c cubed over 3 factorial, plus dot 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 to the nth derivative, x minus c to the n over n factorial. So you see this pattern here. We have some kind of nth derivative. So this is technically the 0th derivative, first derivative, second derivative, third, dot dot dot, nth derivative. Then we have x minus c to the power of that same n, so 0 again, it's fine. 1, so first derivative, power of 1, second derivative, power of 2, third derivative, power of 3, so that's this n. And then divided by, and then again, this is 0 factorial, that's fine, 1 factorial, but it's nth derivative, nth power, nth factorial, nth derivative, n power, n factorial, 3, 3, 3, 1, 1, 1, 2, 2, 2, n, 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 yay. So that's our pattern here. So this is finite. We stop at some degree, n. We just choose it. You could say 10th, n is 10, so 10th derivative times x minus c to the power of 10 divided by 10 factorial. But the important part for this approximation is that n is some kind of constant number. That means that there are more terms in this series if we go infinitely, and that's what makes our error itself. That's why it's an approximation, is instead of going infinitely, we just stop at some degree for an approximation, okay? So this is just a reminder of what the Taylor series part looks like. And then if you just happen to be looking at McLaurin, that just means that c is going to equal 0. And we'll do an example. When we look at this example, I think we can just work it out, and I'll show you what McLaurin looks like, but it's just the same formula, but with c equals 0. So basically x minus 0 goes away to just x. It simplifies it. Also, as a little side note, one time, like way before, someone had mentioned using this dot 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 notation, and they were like trying to shame me for not using like big O notation, but this is math, not like engineering. It's so unnecessary. It was so funny. I don't know if that was this person's intention, but the way that this person wrote it looked like they were trying to pick at something, but honestly, none of my professors, none of my teachers have ever used big O notation in this context. They literally would just do ... because you're doing a series, right? Like, I don't think I've ever seen anyone in a lecture write not in this particular way, so don't come at me for it. But it just seemed like this person was looking for something to pick on. But every time I think about it, because the comment was on a video that had to do with Taylor's series, so this popped up in my mind again. But do whatever makes you happy. But that's what this means, is just we're continuing this series and we're stopping at an end degree, okay? Whatever floats your boat, person. But I'm gonna keep doing this, and so we're gonna do this now. The idea of bounding, this Lagrange Error Bound. So first of all, there's two parts. There's Taylor's theorem and the Lagrange remainder theorem. I don't remember the formal name exactly, but it's this Lagrange Error Bound is from Lagrange's remainder theorem and Taylor's theorem, and sometimes they're used interchangeably. They're basically the same idea, but the general idea is that first you'll start with Taylor's theorem, which says if intuitively you're looking for an error here, because this is an approximation and you're looking for some type of remainder, intuitively it kind of makes sense that it might be related to like the next term in some type of way, the next n plus first derivative. So that's the general idea. Taylor's theorem says that there exists some value z. So there exists, or you can write this as there exists. That's what that means. There exists some z value or some other variable, whatever you want to use, but some z between x and c. So remember, we're finding f of x at some value. In this case, we were doing cosine of 1, right? So between x and c, such that r, sorry, I'm trying to like not make this shake too much, but Rnx. So you're looking basically at the n plus first derivative, and you're doing n plus first of z, and then the rest is that next term, so x minus c to the n plus 1 over n plus 1 factorial. So it's kind of like taking that next n plus first term, but there exists some z between x and c such that this remainder is equal to this. That's Taylor's theorem. And then the next natural little step is for the Lagrange remainder theorem actually bounds this. You want to know what the maximum remainder would be. So the Lagrange remainder theorem is to maximize this. So that just means that we have is less than or equal to the maximum of this part, this maximum of this n plus first derivative at this value z, whatever it may be, x minus c to the n plus 1, the rest is the same, n plus 1 factorial. Okay, so this is, I know it looks like a lot, but hopefully the example can, we can work through one and kind of make some sense out of this, but the general idea is that we just need to find the maximum possible value for this n plus first derivative. So first of all, this z value is just some z that is between x and c, and depending on the function, we don't know if x is bigger or c is bigger, but that doesn't matter. There's just some z value that makes this remainder equal to, and then you're just looking at the n plus first term. And for the actual bound, we just want to maximize that to literally bound that entire error part. So here, we don't actually need to find any particular value of this n plus first derivative or anything like that. We just need to find the maximum possible value. And so it actually oftentimes simplifies a lot, especially when you're doing problems, because especially in this context, because for instance, even for cosine, without working it out, cosine is bounded just naturally by -1 and 1. And also derivatives, right? So your derivatives have to do with sine or negative sine, positive and negative cosine, but sine is also bounded by 1 and -1. So naturally, this is going to work out pretty nicely. And other functions that you're expected to use if you're trying to do this problem relatively quickly, especially on an AP exam or something, it will work out that way as well. Or at least with a little bit of like calculus analysis, you can figure out what this maximum value is. But note that you don't actually have to find the derivative, you just need to know what the maximum value is. So this whole part just kind of goes away. And so it looks complicated and yucky, but it does tend to simplify pretty nicely. Okay, so that's this idea, is the Taylor remainder part just says that there exists some type of z in between x and c such that the remainder after you do this n is equal to the n plus first term. It's like related to the n plus first term, and then Lagrange actually just finds the maximum value of that. Okay, so hopefully that makes sense and is helpful. Alright, so looking at this question, what degree McLaurin series expansion for cosine 1 would have an error less than 0.001? So let's first use this formula that we just wrote out for the Lagrange error bound to answer this question, but then let's go ahead and actually expand this just to see what value we actually get and to also double check our answer. So first of all, in this case, our function is cosine of x. We're looking for cosine 1, but the general function is cosine x. And so this given an x value, in this case the x value is 1. So again, we'll do the actual McLaurin expansion here in a second to double check, but really the point for this question, tying it in with the Lagrange error bound, is that we can just use this formula to say that the remainder is going to be less than or equal to, and here's the interesting part, we're looking at the maximum of the n plus first derivative of this thing. Now, one thing to note is for cosine and for sine, if you look at this pattern here, so we have f of x is cosine x, f prime of x is negative sine of x. And again, we'll do these derivatives again here in a second, but I'm just trying to show you that if you were to write these out kind of quickly, you'll notice that all of the derivatives have simply just cosine and sine in them. And they're just linear here with negatives or positive, right? But with just negative or positive 1 as coefficients, so f prime would be negative, what am I doing? Sine x, and then the fourth derivative is back to cosine x. So there's the cyclical nature. The fifth derivative would be negative sine x again, and so there's the cyclical nature with the derivatives. But the point is that when you take the derivatives here, they're all sine and cosine, and with plus positive 1 or negative 1 coefficients, which means that without doing any calculations here, you know that the maximum of the n plus 1th or n plus 1 degree or order derivative is always going to be 1. That's the cool thing about sine and cosine, is they're bounded. They oscillate between negative 1 and 1, and so they're bounded by this positive 1. So this part, this max part, x minus c, but it's a McLaurin expansion, so c is going to be 0. So you have this x to the n plus 1 over n plus 1 factorial. And then in this case specifically, we're doing this cosine 1 expansion, so we're doing Rn of 1, so x is 1, which means that 1 to the power of anything, and in this case this top part's not going to be 0, actually, but that's still 1, so it actually doesn't even matter. So 1 to the power of anything is 1, so we have 1 over n plus 1 factorial. So what this says is that according to the Lagrange Error Bound, for cosine x, or cosine 1 specifically, the error is going to be less than or equal to 1 over n plus 1 factorial. So if I were to use the McLaurin series expansion for degree, let's say 4, then that error bound, the error is bounded by, so it will be less than or equal to 1 over 5 factorial. So just whatever that n plus 1 factorial. So if the question is then what degree McLaurin series expansion, so in particular I'm assuming we're talking about what's like the first or the smallest degree, what's the first degree that makes the error less than 0.001. So we're kind of working backwards here. We want to know what n makes 1 over n plus 1 factorial less than 0.001. So, in other words, just doing a little algebra here, we want to have n plus 1 factorial be greater than 1 over 0.001, and 1 over 0.001 is, that's going to be 1,000. So basically, what is the first n that makes n plus 1 factorial greater than 1,000? So just off the top of my head, 5 factorial is 120. 6 factorial is 6 times that, which is 720. And so then 7 factorial is surely greater than 1,000, right? So 7 times 620 is like 4,000 something something, so that's definitely greater. So you basically want n plus 1 to equal, or technically anything greater than 7, which means that as long as n is greater than 6, you're good to go. So the actual degree would be 6. And so that would be the very first degree of the McLaurin series, but like we said, any degree greater than that would have an error that's less than 0.001 here. And so that would be our answer just using this. We would say at the least having 6 terms should cover it. But let's take an actual look at this expansion just to get some practice in, and just kind of double check our answer and see how close it actually is. Okay, so if the question is phrased like this in particular, relating, if you're asking for what degree in the context of Lagrange Error Bound, it's really just using this formula here. And so like this part, sometimes you'll see with like a capital M instead, but that's the general idea. It's just the maximum of the n plus 1 or n plus first order derivative. In this case, cosine and sine are very nice to work with, and usually other questions, like I said before, will be pretty straightforward to figure out what that maximum value is. It's not meant to be there to be too complicated. And so that's this part. But let's go ahead and kind of look at this pattern here. So we kind of already wrote out f of x, and then f prime of x, and then f prime prime. So we wrote out some of these derivatives. But let's do it. So for the McLaurin, we again use c equals 0. It's a special case of our Taylor polynomial. So anywhere I see a c here, I'm just going to put 0. So for McLaurin, we have c is 0. So we're doing f of 0 plus f prime of 0. X minus 0 is just x raised to the first power is just x. 1 factorial is just 1. So f prime prime 0, x squared over 2 factorial at 0, x cubed over 3 factorial plus dot dot dot, nth derivative at 0, x to the n over n factorial. Alright, and then, so this is the n approximation, and then of course we have our Rn part, right? The Rn of x, that's the remainder, that's the error part. So here, just for fun, the McLaurin expansion for cosine x is, I mean, at this point you could just look up a table if you wanted to, but since we're already halfway there, f of 0 is cosine of 0, which is 1, so this is 1. F prime of 0 is negative sine 0. Sine 0 is 0, so this actually goes away. 0 times anything is 0. F prime prime 0 is negative cosine of 0, which is negative 1. So negative 1. And of course you can write this out neatly on your own if you want to, but I'm just trying to cover this pattern. F prime prime of 0 is sine 0, and sine 0 is 0, so this whole thing goes away. 0 times anything is 0, so it just goes away. So basically every odd derivative part goes away to 0, and you're only left with 1 and then minus stuff. So 1 minus x squared over 2 factorial, which is 2, but I'll just write that. And then the fourth part will be plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus, and you get the pattern, it's plus minus for only even exponents here, so x to the even 2, 4, 6, 8, 10, and then also in the denominators you have 2 factorial, 4 factorial, 6 factorial, 8 factorial, etc. So if you were to look this up on a table, you might see the sigma notation, and you'll have like negative 1 to the power of stuff to cover the fact that you have plus minus, and then you'll probably have like 2n to do the evens, or 2n plus 1 or something like that, and then with that same part, the denominator factorial, and then you index that depending on how you want to index it, but you might start with like n equals 0 up to n, or if you're doing the full expansion up to infinity, right? But anyway, the whole point is that you have this nice pattern here for the actual expansion. Our answer was that we could go up to 6, a degree of 6 to get an error that's less than 0.001. So remember that they're actually secret in between terms. So if we're going to do up to 6, we're talking about up to this value because we have one term, then we have, so this is kind of like the 0th, but it's like the first term, but then we have the in between, right? The first derivative, second derivative, third, fourth, fifth, sixth. So this would be our 6th piece here, our degree 6. So we would actually stop here for the expansion, and let's see if that is actually true. Remember that we are doing x is 1, so in this case we would estimate with 1 over 2 factorial is 2 plus 1 over 4 factorial is 24 minus 1 over 6 factorial, what do we say that was, 720, right? So for instance, if we were to do just the first one, obviously it's not 1 cosine 1, but if you were to do like degree 2, you would have 1 minus 1/2, which is 0.5. If you were to do degree, of course, like the odd ones are degree 1, degree 3 would just be 0 in between, so the same 4.5, but for 4 you would have 1 minus 1/2 plus 1/24, which is, you can plug that into your calculator just to check. 1 minus 1/2 plus 1 over 24 is 0.5416, repeating. And then for the 6th degree, so like of course which would give you the same thing here. But if you were to do the 6th degree here, it's 1 minus 1 over 2 plus 1 over 24 minus 1 over 720, which is about, so this thing, minus 1 over 720. And also, by the way, just as a little reminder, if you happen to be typing this into a calculator, if you're dealing with a scientific calculator, this will handle the fractions just fine. But if you're going on a calculator from left to right, just make sure you put the parentheses around the divide part. So you'll want to do like 1 minus parentheses 1 over 2 parentheses plus parentheses 1 over 24 parentheses. So you don't want to do like 1 minus 1 is 0 divided by 2 is 0 plus 1 is 1, etc. Right? So just in case you're getting slightly different answers, that might be why. So just don't forget your parentheses in order of operations. But these are the approximations that we get for order 2, 4, and 6, and then order 1, 3, and 5 are going to be the same. So like order 1 will be 1, so order 0 is going to be 1, order 1 will be 1, order 2 will be 0.5, order 3 will also be 0.5 because you're just adding 0, order 4 is going to be this, order 5 is also going to be this, and order 6 is going to be this, because it can be a little confusing since there are missing terms here. Just because they canceled out, that doesn't mean this is degree 4, this is still degree 6. So I just want to remind you of that. This would be our approximation for degree 6, and let's actually check the actual number or actual value. So we have cosine cosine 1, and since we're just by default here, we're going to look at it in radians since we're not given degrees or anything. So in radians we have like something like this, 0.540302305.9, and that keeps going. So that's actually really, really close, right? In fact, if we were to just round this down or up here, it would be 0.5403. That's almost exact. There still is error, but that's pretty good, right? So that's for sure less than 0.001 for an error. Here it's almost but not quite. If we do 0.541666667, let's say, minus 0.5403023-ish, that is 0.0013. That's still technically bigger than 0.001. So we definitely need to go up another degree. So, and not just 1 degree, because we said 5 makes it the same, because that's 0, but we would go up to 6, and so 6 definitely makes the error less than 0.001. So anything greater than that should do it, and it should be sufficient there. I hope that that makes sense. I didn't want to focus too much on actually calculating the McLaurin series expansion, but I hope that this is kind of a nice review. All you have to do is take the Taylor series expansion, do each of the derivatives here just to get an idea for what's going on for your function, in this case cosine, and you take each of the derivatives. And then for McLaurin, you just plug it in at 0 to get the coefficients, the derivative coefficients, and then your actual terms will be x squared, x cubed, x to the 4th, and then you divide by the corresponding factorials. In this case, the odd ones, the odd derivatives, cancel out because they're 0, because they have to do with the sign 0. And then we're left with this pattern of positive, negative, for the even derivatives, starting with 0 actually. So you just start with 1 and then minus, and then you go from there. So yeah, so we actually did the actual approximation, and we confirmed that indeed a degree of 6 should do it. And even though degree of 4 looks pretty good and very close, it doesn't quite hit the 0.001 cutoff. So so this is like a backwards type of question. Otherwise, it might just be to figure out what the error actually is. You might have to calculate some of these approximations. Just kind of keep this in mind, that you're always doing like an actual value, which will be, you know, in your calculator you can find the actual value, and then you approximate it using n degrees of your Taylor-Maclaurin series expansion, and then you find your error from there, okay? So I hope that that helps. If you're given a degree and you want to find the error, you just go ahead and you calculate this and figure out where to stop. And here, this is kind of tricky again. Remember that the degree has to do with the derivative that you're taking, not necessarily the fact that this looks like, you know, 1, 2, 3, 4 terms. This is like the 0th derivative. You have a first one somewhere in between. This is the second, third. There's like a 0 in between, fourth. And so you kind of look at the exponents here, or the n factorial part, to give you a clue for what degree you're talking about. I think that could be kind of confusing, but stop at the degree that you're looking at. So if you're saying what's the error at, you know, degree 6, you would just calculate up to here, and then stop here, and then do your approximation. And then again, in this case, our x value is 1 because we're looking for cosine 1, but if it were cosine whatever else, you just change up the x values, okay? I hope that this helps and kind of gets you more familiar with this topic. Let me know if there's anything else that I can do or clarify or go back through slower. I think at some point I will go through a McLaurin series or a Taylor series polynomial exercise just a little bit slower. Maybe not in this particular context, but maybe just like in another exercise video for fun, just so that we can work on some derivatives and stuff, okay? But otherwise, I hope that this part makes sense. When you do write out the actual theorems, by the way, a lot of times you have to define, you know, what interval we're talking about. So if you're saying like there is an interval, there's some z between x and c, so I'm kind of like writing it out here, paraphrasing it here, but sometimes you have to define what interval you're talking about and kind of write this a little more formally. But this is the idea for both the Taylor remainder theorem and the Lagrange Error Bound. This concept here, whether you see it as like this big M, it's just all the same idea. There is some z between x and z that makes this remainder true. It has to do with the next order derivative, and so this kind of captures that idea. But sometimes you'll see it written out more formally, especially if you revisit the idea in analysis.